convolution algorithm. Myself is Delvina Das, and under the guidance of Dr. Ramanurthy Srinath, Professor, Department of Computer Science, PECIT, Bangalore. So, what will be the overview? Distribution of jobs in a system. Next one is computing the normalizing constant, that is Gn. And the third one is computing performance using Gn. Okay. So, what is the convolution algorithm? The mean value analysis provides a simple algorithm for finding the average queue lengths and response times of various devices in computer systems. Although the average values are sufficient in many cases, sometimes one may want to find more detailed information such as the distribution or variance of queue lengths and response times. For example, in a 2D computer system, one may want to know what the probability is of both disks being busy at the same time, or what the probability is of having more than 5 jobs at a disk. Such questions, which cannot be answered using MVA, can be answered using the convolution algorithm. So, next slide tells about distribution of jobs in a system. The equations used in convolution algorithm are explained in 2 steps. Initially, all service centers in the closed queuing network are assumed to be load independent. That is, the service time per job does not depend upon the queue length. Thus, terminals are not allowed initially. At any instant, the state of such a network is given by the number of jobs at various devices and is represented by the vector n, that equals to n1, n2 up to nn. Here, ni is the number of jobs at the ith device. Gordon and Melville showed that the probability of the system being in state n is P of n1, n2 to up to nn equals to d to the power n1, d2 to the power n2 up to dn to the power nn by gn. Here, di is the service demand per job for the ith device, where n equals to summation of ni is the total number of jobs in the system, and gn is the normalizing constant such that the probabilities for all states add up to 1. So, the equation will be gn equals to summation of d1 to the power n1, d2 to the power n2 up to d to the power nn n. Gn can become too large or too small, causing overflow or underflow. Avoiding by scaling all service demands di's by alpha before computing Gn, let yi equals to alpha di be the scaled service demand for the ith device. Then the equation 1 and 2 become P of n1, n2 up to nn equals to y to the power n1, y2 to the power n2 up to yn to the power nn by gn. And gn equals to summation of y1 to the power n1, y2 to the power n2 up to yn to the power nn. When selecting scaling factors, the scale values should neither be too large nor too small compared to 1. One such choice would be alpha equals to 1 by n summation of i equals to 1 to n di. In any case, the choice of alpha should not affect the probabilities. This example illustrates the use of alpha. Consider this batch computer system consisting of a processor and 2 disks. It can be represented by the closed central server model shown in this figure. The service times are 39 milliseconds per visit to CPU, 180 milliseconds per visit to disk A, and 260 milliseconds per visit to disk B. Each batch job makes 13 I/O requests to disk A and 6 I/O requests to the disk B. We would like to compute the state probabilities when the multiprogramming level is 3. So, the service times are Ace of CPU equals to 0.039, AC equals to 0.18, SP equals to 0.5. to 6. And the visit ratio will be V of CPU equals to 13 plus 6 plus 1 equals to 20, where VA equals to 13 and VB equals to 6. Total surface demands are where D CPU will be V CPU into S CPU, that comes to 0.78. DA will be VA into SA will be 2.34 and DB will come up VB into SB equals to 1.56. For the scaling factor, we arbitrarily choose alpha equals to 1 by 0.78. This results in Y CPU equals to 1, YA equals to 3 and YB equals to 2. The system can be in any state of this state. These states and their probabilities are shown in this table. For each state, we first determine the projection of yi to the power ni, add all the products to find gn and divide each individual product by gn to get the desired probability. Next slide will tell about convolution algorithm for computing gn. The key problem with Gordon and Neville's method, as illustrated by example 1, is that the computation of the normalizing constant requires us to enumerate all possible states. For a system with n jobs and n devices, the number of states is given by n plus n minus 1, n minus 1. This number is of the order of n to the power n minus 1 and is usually very large. Bunsen solved this problem by devising a simple method to compute gn. This method is called convolution and is based on the following mathematical identity, which is true for all k and yi. The equation will be like this way. Here, n is the set of all possible state vectors n1, n2 up to nk such that summation of I equals to 1 to k, ni equals to n. And n is the set of all possible state vectors such that summation of ni equals to n minus 1. The first equation simply breaks the sum into two sums, a sum belonging to states in which nk is 0 and a sum belonging to the remaining states. In equation, the second sum is rewritten so that yk, which is common to all terms in the second sum, is factored out. So, consider the central sorted model of example 1. To compute gn, we need to compute the following sum. Gn equals to y1 to the power 0, y2 to the power 0, y3 to the power 3 plus y10, y21, y3 square plus y10, y2 square, y31 this way, and the power of y's in the above sum corresponding to the 10 states specified by number of jobs at various devices will be gn equals to y10, y2 to the power 3 plus y1, y2 square plus y1 whole square, y21 plus y1 to the power 3, y20 plus y3 into y10, y20, y3 square plus y1 to the power 0, y2 to the power 1, y3 to the power 1 plus y10, y2 square, y30 plus y11, y20, y31 plus y11, y21, y30 plus y11, y20, y30. By separating out the terms containing y30, the above sum can be rewritten as follows. Like gn equals to y1 to the power 0, y2 to the power 3, y3 to the power 0 plus y11, y2 square, y30 this way. Since y3 is common to all terms in the second part, the sum can also be written as gn equals to y10, y2 to the power 3 plus y11, y2 square plus y1 square, y21 plus y1 to the power 3, y20 this way. Notice that the first part contains terms corresponding to the state instead of 3. If we define g of nk as follows, like g of nk equals to summation of projection of I equals to 1 to k while I to the power n I, then g of nk will be g of n comma k minus 1 plus yk into g of n minus 1 comma k. The initial values for the auxiliary function are g of n comma 0 equals to 0, n equals to 1 comma 2 comma up to n, and g of 0 comma k equals to 1 where k equals to 1 to up to n. This results in a simple algorithm for computing g of n comma n. A tabular representation of this algorithm is shown in this table. The table has n plus 1 rows and n columns. The rows are numbered 0 to n. The ith row corresponds to n equals to I jobs in the system, and the jth column corresponds to the jth service facility. The n comma k entry in the table is g of n comma k. It is obtained by adding together by the value immediately to its left and the value immediately above multiplied by the corresponding column variable yk. Generally, only the rightmost column values are of interest, and therefore it is not necessary to store the complete table. It is sufficient to store just one column, that is g of 0, comma g of 1 up to g of n, and use the following algorithm, where for k equals to 1 to n do, for n equals to 1 to n do, g of n will be g of n plus y of k into g of n minus 1. Consider the central circular model of example 1 again. Using the convolution algorithm, we can compute Gn as shown in table, this one. The first row of the table is initialized to all ones. The first column consists of successive powers of y1, which in this case happens to be 1. Each of the remaining entries is obtained using the entry to its left and entry above in its equation. For the example, 1 plus 3 cross 1 gives 4, 1 plus 3 cross 4 gives 13, 1 plus 3 cross 13 gives 40, 4 plus 2 cross 1 gives 6, and so on. So, how to compute performance using Gn? Once the G1 up to Gn are known, other performance statistics can be computed as follows. First one is Q-length distribution. The probability of having J or more jobs at the ith device is given by probability of in I greater than equals to J equals to summation of y1 to the power n1, y2 to the power n2 up to yn to the power nn by Gn, where in I will be greater than equals to J, that equals to yi to the power j, g of n minus j by g of n. The probability of exactly j jobs at the ith device is p of n I equals to j equals to probability of n I greater than equals to j minus probability of n I greater than equals to j plus 1. That will come ya to the power j by gn into g of n minus j minus g of n minus j minus 1. The mean number of jobs at the ith device, expectation of n I is given by qi equals to e of n I equals to summation of j equals to 1 to n, probability of n I greater than equals to j equals to summation of j equals to 1 to n yi to the power j g n minus j by g n. Next, the joint probability of having j or more jobs at the ith device and l or more jobs at kth level device is given by p of ni greater than equals to j, nk greater than equals to l equals to yi to the power j, yk to the power l, g of n minus j minus l by gn. And the utilization is given by where the device utilization is the same as the probability of having one or more jobs at the device, where it can be given by ui equals to probability of ni greater than equals to 1 equals to yi g of n minus 1 by g of n. And the throughput will be given by from utilization law xi equals to ui by si. The system throughput is given by the forced flow law, that is x equals to xi by vi equals to ui by di equals to alpha into g of n minus 1 by gn. The response time will be given by where the mean response time of a device is given by Newton law, Ri equals to qi by xi equals to qi by xvi. The mean system response time is given by the general response time law, where R equals to summation of I equals to 1 to n Ri Vi. We now illustrate the algorithm using an example. Consider the central servo model of example 1. For this system, G1 is 6, G2 is 25 and G3 is 90. Q-length distribution will be the probability of having 2 or more jobs at disk A is probability of Na greater than equals to 2 equals to ya square g of n minus 2 by gn equals to 3 square into 6 by 90, that will come 0.6. The probability of exactly one job at this K is probability of Na equals to 1, that is ya by g of n into g of n minus 1 minus ya g of n minus 2. That will come 3 by 90 into 25 minus 3 into 6, that equals to 0.233. The probability of exactly 0, 2 and 3 jobs at disk A can be similarly computed, where probability of n equals to 0, where the equation will be ya to the power 0 by gn into g of n minus 0, as because n equals to 0, minus ya g of n minus 1, it will come 0.166. And probability of n equals to 2, where you can see that g of n minus 2 minus ya g of n minus 3 by gn, that will come 0.3. And probability of n equals to 3, where we can see n equals to 3 in g of n minus 3 and ya of g into n minus 4, it will come 0.3. Now that we have a complete distribution of Q length at disk A, we can compute its mean, variance and any higher order statistics, where E of Na equals to summation of j equals to 1 to n j into P of Na equals to j, it will come 1.733. E of n square A, it will come summation of j equals to 1 to n j square P of Na equals to j, it will come 4.133. And variance of Na equals to E of n square A minus E of Na whole to the power square, that will come 4.133 minus 1.733 square equals to 1.33. The probability that both disks are busy is given by the joint probability of having one or more jobs at disk A and one or more jobs at disk B. That is P of Na greater than equals to 1, Nb greater than equals to 1 equals to ya yb into g of n minus 2 by gn equals to 3 into 2 into 6 by 90, it will be 0.4. The mean Q length at the three service centers are Q of CPU, that will be summation of j equals to 1 to n y to the power j's of CPU into g of n minus j by jn, it will come 0.356, we can see. QA will be summation of j equals to 1 to n ya to the power j into g of n minus j by gn, where it will come the value 1.733. And QB equals to summation of j equals to 1 to the power n yb to the power j g of n minus j by gn 0.911. As a check, note that the 3Q lengths sum up to 3, which is the total number of jobs in the system. Utilization. The CPU utilization is U of CPU equals to P of n CPU, that is greater than equals to 1, equals to Y of CPU into G of n minus 1 by G of n. It will come 0.278. The throughput, the system throughput is X equals to alpha into G of n minus 1 by Gn equals to 1 by 0.78 into 25 by 90 equals to 0.356 jobs per second. The CPU throughput will be X of CPU equals to X V CPU equals to 0.356 into 20, that equals to 7.1 jobs per second. The response time. The mean response time of the three devices are R of CPU equals to Q of CPU by X V CPU. We can compute it, which will come 0.05 seconds. RA will be QA by X into VA, which will come 0.37 seconds, and RB, that is equals to QB by X VB, that will come 0.43 seconds. The mean system response time as given by the general response time law is R equals to summation of Ri into Vi, that equals to 0.05 into 20 plus 0.37 into 30 plus 0.43 into 6 equals to 8.42 seconds. As a check, we can use Little's law to find the mean number of jobs in the system. That is N equals to XR equals to 0.356 into 8.42, that equals to 3. So the recap is, as a check, we can use Little's law to find the mean number of jobs in the system, that is P of n1, n2 up to n of n, that will come d1 to the power n1, d2 to the power n2 up to d to the power n by gn. A system with n jobs and n devices has approximately n to the power n minus 1 states. Convolution algorithm allows Gn to be computed using n computations, where G of nk equals to G of n, k minus 1 plus Yk into G of n minus